Good morning. My name is Will Kleber, and I will talk about inference of memory bounds. The goal of this project is to detect the intended bounds that given pointers should be able to access. This solves two unrelated problems. The first problem is repairing buffer security vulnerabilities. This includes both out-of-bounds writes, for example, traditional buffer overflows, as well as out-of-bounds reads that can leak sensitive information, which is a relatively newer problem. A prime example of out-of-bounds reads leaking information is Heartbleed from a few years ago, which that vulnerability could be used to compromise the SSL private keys of 2/3 of all websites, so it was a very severe vulnerability. And furthermore, it was unaffected by mitigations such as address space layout randomization and data execution prevention. In the general case, we have a reusable buffer with stale sensitive data, and in that case, reads should be bounded to the valid portion of the array. This affects even memory-safe languages. For example, the Jetty web server, written in Java, was found to leak passwords and other sensitive information. As an example, let's consider a web server with a reusable buffer. After processing a first request, the buffer is tainted with sensitive data from the request. Then suppose that a second request comes in, and the web server partially overwrites the buffer, but if the second request is smaller than the first, then you still have stale, potentially sensitive data in the buffer from the first request. So the upper bound for reading from the buffer should be the most recently written position of the buffer, which corresponds to the end of the second request. The second problem that this project addresses is decompilation of binaries. To help the analyst understand the meaning of a decompiled program, we will reconstruct information of the form: the bounds of a pointer p is the interval from n to m. Our approach is to first apply static analysis to find and evaluate likely bounds. For decompilation, we will report these bounds, and we can also use this information to give more meaningful names to variables that represent the lengths of arrays. For repair of program source code, we will perform dynamic analysis to validate the results of our static analysis, and then we will repair the program to insert missing bounds checks. So the first step of our approach is to perform static analysis to identify qualifying arrays. Then we will do another static analysis to identify candidate bounds. Next, we will perform dynamic analysis to confirm or reject these candidate bounds. And finally, we will transform the program so that it would abort if a bounds check fails. We have several strategies for proposing candidate bounds, and the one that I will focus on is the first one here. For reads, the most recent written position of the buffer will be considered a candidate upper bound for reading from the array. We use dynamic analysis to confirm or reject candidate bounds, and the way that we do that is we run the program on presumed good runs and see what memory is actually accessed on those traces. So the first step of doing this is to instrument the program to record in a log file which checks are violated, as well as statistics on the checks that succeed. The next step is to run the program to collect presumed good traces, and then we will divide the bounds checks into three categories: those that are strongly supported, meaning that there are many traces where the bounds check succeeds, and also that the values are close to the bound, and there are no failed checks. The second category is bounds checks that are likely incorrect, and a bounds check is in that category if there are traces where it fails, where the check is violated. And the third category, indeterminate, is traces or bound checks where there is insufficient log data to place the check in either one of the two above categories. Finally, we repair the program to insert missing bounds checks. So how do we determine which arrays should be subject to the analysis for reading outside the valid portion of an array? Well, as a heuristic, we consider an array to be a qualifying array if and only if every write to the array is either at index 0, the beginning of the array, or at the successor of the last written position. So how do we identify what the valid portion of an array is? Our heuristic is that it is from the beginning of the array up to and including the last written position of the array. So now, one might wonder, how often do qualifying arrays occur in real-world programs? To establish the ground truth of this matter, we do a separate dynamic analysis, which I'll discuss next. So we build upon SafeCode, which uses the LLVM compilation process. SafeCode maintains a side table that records the size and location of allocated memory regions, and it does bounds checking on pointer arithmetic to prevent invalid memory accesses, reading outside the buffer itself. So we have extended SafeCode as follows. We extended it to record the last written position of each allocated array and to check whether each write of the array is consistent with the definition of a qualifying array. If so, if all writes have been qualifying, then we flag any reads beyond the last written position of the array. This has two purposes. The first is to validate the static analysis, and secondly, it can also be used independently as a source-to-binary repair. In that case, it would be, you will have a higher runtime overhead than if you do static analysis, but it can still be useful in cases where performance is not critical. Here we see a finite state machine diagram of this analysis. When a program writes to an array, we check to see whether it's at index 0 or the successor of the last written position, in which case we update the last written position, and otherwise we mark the array as non-qualifying. For a read, we check to see if the array is qualifying, and if you're reading beyond the last written position, in which case we flag the access. So as mentioned, Jetty is a web server that leaks passwords from a reused buffer. We have implemented a dynamic analysis for Java programs with byte buffers that dynamically patch the program to prevent leakage of that sensitive information. So here we see a diagram of unpatched Jetty. So the attacker sends a specially crafted malformed request, which triggers a bug. It triggers a bug in Jetty when Jetty builds the error message that it would supply to the attacker, and that bug causes Jetty to read past the last written position of the array. It reads stale sensitive data and sends that sensitive data to the attacker. So after we have patched Jetty, we detect when Jetty is reading past the valid portion of the array. We detect that, and then we terminate Jetty so that no information is leaked to the attacker. So in conclusion, this work repairs spatial memory violations with a focus on out-of-bounds reads that leak sensitive information. This project is the first part of a 4-year project on automated repair, and our ultimate goal is to enable a proof of memory safety. And proving memory safety is actually part of a larger thrust in automated code repair. And here, the ultimate goal is to enable cost-effective remediation of defects in large DoD code bases. Are there any questions?
Thank you. How does this work compare to the work that was done under the recently completed DARPA Cyber Grand Challenge?
Okay, so there has been work on the DARPA Grand Challenge to patch binaries as they're running. And most of that work has been focused on, if you have a buffer, traditional buffer overflow is where you read outside the buffer itself. So that has been the focus of this DARPA Grand Challenge. Whereas in this project, we focused on not reading outside of the buffer, reading inside the buffer, but reading stale data in that buffer. So that's the main difference. We are focusing on reads that are still within the buffer, but reads that read sensitive information from a previous request, whereas most of the DARPA Grand Challenge work has focused on memory safety violations of reading outside the buffer itself.